By now, you've seen a couple different learning algorithms, linear regression and logistic regression. They work well for many problems, but when you apply them to certain machine learning applications, they can run into a problem called overfitting that can cause them to perform very poorly. What I'd like to do in this video is explain to you what is this overfitting problem, and in the next few videos after this, we'll talk about a technique called regularization that will allow us to ameliorate or to reduce this overfitting problem and get these learning algorithms to maybe work much better. So what is overfitting? Let's keep using our running example of predicting housing prices with linear regression, where we want to predict the price as a function of the size of the house. One thing we could do is fit a linear function to this data, and if we do that, maybe we get that sort of straight line fit to the data. But this isn't a very good model. Looking at the data, it seems pretty clear that as the size of the house increases, the housing prices plateau or kind of flattens out as we move to the right. And so this algorithm doesn't fit the training set very well, and we call this problem underfitting. And another term for this is that this algorithm has high bias. Both of these roughly mean that it's just not even fitting the training data very well. The term bias is kind of a historical or technical one, but the idea is that if we're fitting a straight line to the data, then it's as if the algorithm has a very strong preconception or a very strong bias that housing prices are going to vary linearly with their size. And despite the data to the contrary, despite the evidence to the contrary, its preconceptions still, or bias still causes it to fit a straight line, and this ends up being a poor fit to the data. Now, in the middle, we could fit a quadratic function to the data, and with this data set, we fit a quadratic function, maybe we get that kind of curve, and that works pretty well. And at the other extreme would be if we were to fit, say, a fourth order polynomial to the data. So here we have 5 parameters, theta 0 through theta 4, and with that, we can actually fit a curve that passes through all 5 of our training examples. We might get a curve that looks like this, that on the one hand seems to do a very good job fitting the training set, and it passes through all of my data at least, but this is sort of very wiggly curve, right? Sort of going up and down all over the place, and we don't actually think that's such a good model for predicting housing prices. So this problem we call overfitting, and another term for this is that this algorithm has high variance. The term high variance is another sort of historical or technical one, but the intuition is that if we're fitting such a high order polynomial, then the hypothesis can fit, it's almost as if it can fit almost any function, and the space of possible hypotheses is just too large, or it's too variable, and we don't have enough data to constrain it to give us a good hypothesis. So that's called overfitting. And in the middle, there isn't really a name, but I'm just going to write, just right, where a second degree polynomial, a quadratic function, seems to be just right for fitting this data. To recap a bit, the problem of overfitting comes when, if we have too many features, then the learned hypothesis may fit the training set very well. So your cost function may actually be very close to 0, or maybe even 0 exactly. But you may then end up with a curve like this that tries too hard to fit the training set, so that it even fails to generalize to new examples, that it fails to predict prices on new examples well. And here the term generalize refers to how well a hypothesis applies even to new examples, that is, to data, to houses that it hasn't seen in the training set. On this slide, we looked at overfitting for the case of linear regression. A similar thing can apply to logistic regression as well. Here's a logistic regression example with 2 features, x1 and x2. One thing we could do is fit logistic regression with just a simple hypothesis like this, where, as usual, g is my sigmoid function. And if you do that, you end up with the hypothesis trying to use maybe just a straight line to separate the positive and the negative examples. And this doesn't look like a very good fit to the hypothesis. And so, once again, this is an example of underfitting or of a hypothesis having high bias. In contrast, if you were to add to your features these quadratic terms, then you could get a decision boundary that might look more like this. And that's a pretty good fit to the data. Probably about as good as we could get on this training set. And finally, at the other extreme, if you were to fit a very high order polynomial, if you were to generate lots of high order polynomial terms as features, then logistic regression may contort itself, may try really hard to find a decision boundary that fits your training data, or go to great lengths to contort itself to fit every single training example well. And if the features x1 and x2 are for predicting maybe the cancerous, malignant, benign breast tumors, this really doesn't look like a very good hypothesis for making predictions. And so once again, this is an instance of overfitting and of the hypothesis having high variance and being unlikely to generalize well to new examples. Later in this course, when we talk about debugging and diagnosing things that can go wrong with learning algorithms, we'll give you specific tools to recognize when overfitting and also when underfitting may be occurring. But for now, let's talk about the problem of if we think overfitting is occurring, what can we do to address it? In the previous examples, we had 1 or 2 dimensional data, so we could just plot the hypothesis and see what was going on and select the appropriate degree polynomial. So earlier, for the housing prices example, we could just plot the hypothesis and maybe see that it was fitting this sort of very wiggly function that goes all over the place to predict housing prices, and we could then use figures like these to select an appropriate degree polynomial. So plotting the hypothesis could be one way to try to decide what degree polynomial to use, but that doesn't always work. And in fact, more often, we may have learning problems where we just have a lot of features. And there is not just a matter of selecting what degree polynomial, and in fact, when we have so many features, it also becomes much harder to plot the data and becomes much harder to visualize it, to decide what features to keep or not. So concretely, if we're trying to predict housing prices, sometimes we can just have a lot of different features, and all of these features seem, maybe they seem kind of useful. But if we have a lot of features and very little training data, then overfitting can become a problem. In order to address overfitting, there are 2 main options for things that we can do. The first option is to try to reduce the number of features. Concretely, one thing we could do is manually look through the list of features and use that to try to decide which are the more important features, and therefore which are the features we should keep and which are the features we should throw out. Later in this class, we'll also talk about model selection algorithms, which are algorithms for automatically deciding which features to keep and which features to throw out. This idea of reducing the number of features can work well and can reduce overfitting. And when we talk about model selection, we'll go into this in much greater depth. But the disadvantage is that by throwing away some of the features is also throwing away some of the information you have about the problem. For example, maybe all of those features are actually useful for predicting the price of a house, so maybe we don't actually want to throw some of our information or throw some of our features away. The second option, which we'll talk about in the next few videos, is regularization. Here, we're going to keep all the features, but we're going to reduce the magnitude or the values of the parameters theta j. And this method works well, we'll see, when we have a lot of features, each of which contributes a little bit to predicting the value of y, like we saw in the housing price prediction example, where we could have a lot of features, each of which are somewhat useful, so maybe we don't want to throw them away. So this describes the idea of regularization at a very high level, and I realize that all of these details probably don't make sense to you yet. But in the next video, we'll start to formulate exactly how to apply regularization and exactly what regularization means. And then we'll start to figure out how to use this to make our learning algorithms work well and avoid overfitting. In this video, I'd like to convey to you the main intuitions behind how regularization works, and we'll also write down the cost function that we'll use when we're using regularization. With the hand-drawn examples that we'll have on these slides, I think I'll be able to convey part of the intuition, but an even better way to see for yourself how regularization works is if you implement it and sort of see it work for yourself. And if you do the programming exercises after this, you get a chance to sort of see regularization in action for yourself. So here's the intuition. In the previous video, we saw that if we were to fit a quadratic function to this data, it gives us a pretty good fit to the data. Whereas if we were to fit an overly high order degree polynomial, we end up with a curve that may fit the training set very well, but really not overfit the data poorly and not generalize well. Consider the following. Suppose we were to penalize and make the parameters theta 3 and theta 4 really small. Here's what I mean. Here's our optimization objective, or here's an optimization problem where we minimize our usual squared error cost function. Let's say I take this objective and I modify it and add to it plus 1000 theta 3 squared plus 1000 theta 4 squared. 1000 I'm just writing down as some huge number. Now, if we were to minimize this function, well, the only way to make this new cost function small is if theta 3 and theta 4 are small, right? Because otherwise, if you have 1000 times theta 3, this new cost function is going to be big. So when we minimize this new function, we're going to end up with theta 3 close to 0 and theta 4 close to 0. And that's as if we're getting rid of these two terms over there. And if we do that, well then, if theta 3 and theta 4 are close to 0, then we're basically left with a quadratic function. And so we'll end up with a fit to the data that's, a quadratic function plus maybe tiny contributions from small terms, theta 3, theta 4, that are maybe very close to 0. Maybe. And so we end up with essentially a quadratic function, which is good because it's a much better hypothesis. In this particular example, we looked at the effect of penalizing two of the parameter values being large. More generally, here's the idea behind regularization. The idea is that if we have small values for the parameters, then having small values for the parameters will usually correspond to having a simpler hypothesis. So for our last example, we penalized just theta 3 and theta 4, and when both of these were close to 0, we wound up with a much simpler hypothesis that was essentially a quadratic function. But more broadly, if we penalize all the parameters, usually that we can think of that as trying to give us a simpler hypothesis as well, because when these parameters are close to 0, in this example, that gave us a quadratic function. But more generally, it's possible to show that having smaller values of the parameters corresponds to usually smoother functions as well that are simpler, and which are therefore also less prone to overfitting. I realized that the reasoning for why having all the parameters be small, why that corresponds to a simpler hypothesis, I realized that reasoning may not be entirely clear to you right now, and it is kind of hard to explain unless you implement it yourself and see it for yourself. But I hope that the example of having theta 3 and theta 4 be small and how that gave us a simpler hypothesis, I hope that helps explain why, at least give some intuition as to why this might be true. Let's look at a specific example. For housing price prediction, we may have our 100 features that we talked about, where maybe x1 is the size, x2 is the number of bedrooms, x3 is the number of floors, and so on, and we may have 100 features. And unlike the polynomial example, we don't know, right? We don't know that theta 3, theta 4 are the high-order polynomial terms. So if we have just if we have just a set of 100 features, it's hard to pick in advance which are the ones that are less likely to be relevant. So we have, 100 or 101 parameters, and we don't know which ones to pick. We don't know which parameters to pick to try to shrink. So in regularization, what we're going to do is take our cost function. Here's my cost function for linear regression. And what I'm going to do is modify this cost function to shrink all of my parameters because I don't know which one or two to try to shrink. So I'm going to modify my cost function to add a term at the end, like so. Let me add square brackets here as well. I'm going to add an extra regularization term at the end to shrink every single parameter. And so this term will tend to shrink all of my parameters, theta 1, theta 2, theta 3, up to theta 100. By the way, by convention, the summation here starts from 1. So I'm not actually going to penalize theta 0 being large. That's sort of a convention that the sum is from I equals 1 through n rather than I equals 0 through n. But in practice, it makes very little difference. And whether you include theta 0 or not, in practice, it'll make very little difference to the results. But by convention, usually we regularize only theta 1 through theta 100. Writing down our regularized optimization objective, our regularized cost function again, here it is. Here's j of theta, where this term on the right is the regularization term, and lambda here is called the regularization parameter. And what lambda does is it controls a trade-off between two different goals. The first goal, captured by the first term in the objective, is that we would like to fit the training data well. We would like to fit the training set well. And the second goal is we want to keep the parameters small, and that's captured by the second term, by the regularization objective, and by the regularization term. And what lambda, the regularization parameter, does is it controls the trade-off between these two goals, between the goal of fitting the training set well and the goal of keeping the parameters small, and therefore keeping the hypothesis relatively simple to avoid overfitting. For our housing price prediction example, whereas previously if we had fit a very high order polynomial, we may have wound up with a very sort of wiggly or curvy function like this. If you still fit a high order polynomial with all the polynomial features in there, but instead you just make sure to use this sort of regularized objective, then what you can get out is in fact a curve that isn't quite a quadratic function, but is much smoother and much simpler, and maybe a curve like the magenta line that fits, that gives a much better hypothesis for this data. Once again, I realize it can be a bit difficult to see why shrinking the parameters can have this effect, but if you implement this algorithm yourself with regularization, you will be able to see this effect firsthand. In regularized linear regression, if the regularization parameter lambda is said to be very large, then what will happen is we will end up penalizing the parameters theta 1, theta 2, theta 3, theta 4 very highly. That is, if our hypothesis is this one down at the bottom. And if we end up penalizing theta 1, theta 2, theta 3, theta 4 very heavily, then we'll end up with all of these parameters close to 0, right? Theta 1 will be close to 0, theta 2 will be close to 0, theta 3 and theta 4 will end up being close to 0. And if we do that, it's as if we're getting rid of these terms in our hypothesis, so that we're just left with a hypothesis that looks like that. It says that, well, housing prices are equal to theta 0, and that is akin to fitting a flat horizontal straight line to the data. And this is an example of underfitting. And in particular, this hypothesis, this straight line, it just fails to fit the training set well. It's just a flat straight line. It doesn't go, it doesn't go anywhere near most of our training examples. And another way of saying this is that this hypothesis has too strong a preconception or too high a bias that housing prices are just equal to theta 0. And despite the clear data to the contrary, it chooses to fit this sort of flat line, just a flat horizontal line. I didn't draw that very well. Fits just a horizontal flat line to the data. So for regularization to work well, some care should be taken to choose a good choice for the regularization parameter lambda as well. And when we talk about model selection later in this course, we'll talk about a variety of ways for automatically choosing the regularization parameter lambda as well. So that's the idea behind regularization and the cost function we'll use in order to use regularization. In the next two videos, let's take these ideas and apply them to linear regression and to logistic regression so that we can then get them to avoid overfitting problems. For linear regression, we had previously worked out two learning algorithms, one based on gradient descent and one based on the normal equation. In this video, we'll take those two algorithms and generalize them to the case of regularized linear regression. Here's the optimization objective that we came up with last time for regularized linear regression. This first part is our usual objective for linear regression, and we now have this additional regularization term where lambda is our regularization parameter, and we like to find parameters theta that minimizes this cost function, this regularized cost function j of theta. Previously, we were using gradient descent for the original cost function without the regularization term, and we had the following algorithm. For regular linear regression without regularization, we will repeatedly update the parameters theta j as follows for j equals 0, 1, 2, up through n. Let me take this and just write the case for theta 0 separately. So, I'm just going to write the update for theta 0 separately then for the update for the parameters 1, 2, 3, and so on up to n. And this is, I haven't changed anything yet, right? This is just writing the update for theta 0 separately from the updates for theta 1, theta 2, theta 3, up to theta n. And the reason I want to do this is you may remember that for our regularized linear regression, we penalize the parameters theta 1, theta 2, and so on up to theta n, but we don't penalize theta 0. So when we modify this algorithm for regularized linear regression, we're going to end up treating theta 0 slightly differently. Concretely, if we want to take this algorithm and modify it to use the regularized objective, all we need to do is take this term at the bottom and modify it as follows. I'm going to take this term and add minus lambda over m times theta j. And if you implement this, then you have gradient descent for trying to minimize the regularized cost function j of theta. And concretely, I'm not going to sort of do the calculus to prove it, but concretely, if you look at this term that written in square brackets, if you know calculus, it's possible to prove that that term is the partial derivative with respect to j of theta using the new definition of j of theta with the regularization term. And similarly, this term up on top, which I guess I'm drawing the cyan box, that's still the partial derivative with respect to theta 0 of j of theta. If you look at the update for theta j, it's possible to show something pretty interesting. Concretely, theta j gets updated as theta j minus alpha times, and then you have this other term here that depends on theta j. So if you group all the terms together that depend on theta j, you can show that this update can be written equivalently as follows. And all I did was that theta j here is theta j times 1, and this term is lambda over m. There's also an alpha here, so you end up with alpha lambda over m multiplied into theta j. And this term here, 1 minus alpha times lambda m, is a pretty interesting term. It has a pretty interesting effect. Concretely, this term 1 minus alpha times lambda over m is going to be a number that's, usually it's a number that's usually like a little bit less than 1, right? Because alpha times lambda over m is going to be positive. And usually, if your learning rate is small and if m is large, this is usually pretty small. So this term here is going to be a number that's usually, a little bit less than 1. So think of it as a number like 0.99, let's say. And so the effect of our update to theta j is we're going to say that theta j gets replaced by theta j times 0.99, right? So theta j times 0.99 has the effect of shrinking theta j a little bit towards 0. So this makes theta j a bit smaller. Or more formally, this makes the squared norm of theta j a little bit smaller. And then after that, the second term here, that's actually exactly the same as the original gradient descent update that we had before we added all this regularization stuff. So hopefully this gradient descent, hopefully this update makes sense. When we're using regularized linear regression, what we're doing is on every iteration, we're multiplying theta j by a number that's a little bit less than 1, so we're shrinking the parameter a little bit, and then we're performing, similar update as before. Of course, that's just the intuition behind what this particular update is doing. Mathematically, what it's doing is exactly gradient descent on the cost function j of theta that we defined on the previous slide that uses the regularization term. Gradient descent was just one of our two algorithms for fitting a linear regression model. The second algorithm was the one based on the normal equation, where what we did was we created the design matrix X, where each row corresponded to a separate training example, and we created a vector Y. So this is a vector that's an m-dimensional vector, and that contained the labels from a training set. So whereas X is an m by n plus 1 dimensional matrix, Y is a m-dimensional vector. And in order to minimize the cost function j, we found that one way to do so is to set theta to be equal to this, right? We had X transpose X inverse X transpose Y. I'm leaving room here to fill in stuff, of course. And what this value for theta does is this minimizes the cost function j of theta when we were not using regularization. Now that we are using the regularization, if you were to derive what the minimum is, and just to give you a sense of how to derive the minimum, the way you derive it is you take partial derivatives with respect to each parameter, set this as 0, and then do a bunch of math, and you can then show that it's a formula like this that minimizes the cost function. And concretely, if you are using regularization, then this formula changes as follows. Inside this parenthesis, you end up with a matrix like this, 0, 1, 1, 1, and so on, 1 until the bottom. So this thing over here is a matrix whose upper leftmost entry is 0, the 1's on the diagonals, and then the 0's everywhere else in this matrix, because I'm drawing this a little bit sloppily. But as a concrete example, if n equals 2, then this matrix is going to be a 3 by 3 matrix. More generally, this matrix is a n plus 1 by n plus 1 dimensional matrix. So if n equals 2, then that matrix becomes something that looks like this. It would be 0, and then 1's on the diagonals, and then 0's on the rest of the off diagonals. And once again, I'm not going to show this derivation, which is frankly somewhat long and involved, but it's possible to prove that if you are using the new definition of j of theta with the regularization objective, then this new formula for theta is the one that would give you the global minimum of j of theta. So finally, I want to just quickly describe the issue of non-invertibility. This is relatively advanced material, so you should consider this as optional, and feel free to skip it, or if you listen to it and parts of it don't really make sense, don't worry about it either. But earlier when I talked about the normal equation method, we also had an optional video on the non-invertibility issue. So this is another optional part that's sort of an add-on to that earlier optional video on non-invertibility. Now, consider a setting where m, the number of examples, is less than or equal to n, the number of features. If you have fewer examples than features, then this matrix, X transpose X, will be non-invertible, or singular, or the other term for this is the matrix will be degenerate. And if you implement this in Octave anyway, and you use the pin function to take the pseudo-inverse, it'll kind of do the right thing, but it's not clear that it'll give you a very good hypothesis, even though numerically, the Octave pin function will give you a result that kind of makes sense. But if you were doing this in a different language, and if you were taking just the regular inverse, which in Octave is denoted with the function inv, if you're trying to take the regular inverse of X transpose X, then in this setting, you find that X transpose X is singular, is non-invertible, and if you're doing this in a different programming language and using some linear algebra library to try to take the inverse of this matrix, it just might not work because that matrix is non-invertible or singular. Fortunately, regularization also takes care of this for us, and concretely, So long as the regularization parameter lambda is strictly greater than 0, it is actually possible to prove that this matrix, x transpose x plus lambda times this funny matrix here, is possible to prove that this matrix will not be singular and that this matrix will be invertible. So using regularization also takes care of any non-invertibility issues of the x transpose x matrix as well. So you now know how to implement regularized linear regression. Using this, you'll be able to avoid overfitting even if you have lots of features and a relatively small training set, and this should let you get linear regression to work much better for many problems. In the next video, we'll take this regularization idea and apply it to logistic regression so that you'll be able to get logistic regression to avoid overfitting and perform much better as well. For logistic regression, we previously talked about two types of optimization algorithms. We talked about how to use gradient descent to optimize this cost function j of theta, and we also talked about advanced optimization methods, ones that require that you provide a way to compute the cost function j of theta and that you provide a way to compute the derivatives. In this video, we'll show how you can adapt both of those techniques, both gradient descent and the more advanced optimization techniques, in order to have them work for regularized logistic regression. So here's the idea. We saw earlier that logistic regression can also be prone to overfitting if you fit it with a very sort of high order polynomial features like this, where g is the sigmoid function, and in particular you may end up with a hypothesis whose decision boundary is this sort of a overly complex, extremely contorted function that really isn't such a great hypothesis for this training set. And more generally, if you have logistic regression with a lot of features, not necessarily polynomial ones, but just with a lot of features, you can end up with overfitting. This was our cost function for logistic regression, and if we want to modify it to use regularization, all we need to do is add to it the following term plus lambda over 2m, sum from j equals 1, and as usual, from 1, sum from j equals 1 rather than sum from j equals 0 of theta j squared, and this has the effect, therefore, of penalizing the parameters theta 1, theta 2, and so on, up to theta n from being too large. And if you do this, then it will have the effect that even though you're fitting a very high order polynomial with a lot of parameters, so long as you apply regularization and keep the parameters small, you're more likely to get a decision boundary that maybe looks more like this and looks more reasonable for separating out the positive and the negative examples. So when using regularization, even when you have a lot of features, the regularization can help take care of the overfitting problem. How do we actually implement this? Well, for the original gradient descent algorithm, this was the update we had. We would repeatedly perform the following update to theta j. This slide looks a lot like the previous one for linear regression, but what I'm going to do is write the update for theta 0 separately. So the first line is my update for theta 0, and the second line is now my update for theta 1 up to theta n, because I'm going to treat theta 0 separately. And in order to modify this algorithm to use the regularized cost function, all I need to do is pretty similar to what we did for linear regression, is actually to just modify this second update rule as follows. And once again, this cosmetically looks identical to what we had for linear regression, but of course is not the same algorithm as we had, because now the hypothesis is defined using this. So this is not the same algorithm as regularized linear regression, because the hypothesis is different. Even though this update that I wrote down, it actually looks cosmetically the same as what we had earlier when working out gradient descent for regularized linear regression. And of course, just to wrap up this discussion, this term here in the square brackets, so this term here, this term is of course the new partial derivative with respect to theta j of the new cost function j of theta, where j of theta here is the cost function we defined on the previous slide that does use regularization. So that's gradient descent for regularized linear regression. Let's talk about how to get regularized linear regression to work using the more advanced optimization methods. And just to remind you, For those methods, what we needed to do was to define a function, that's called the cost function, that takes as input a parameter vector theta. And once again, in the equations we've been writing here, we use 0 index vectors. So we had theta 0 up to theta n. But because octave indexes the vectors starting from 1, theta 0 is written in octave as theta 1 is written in octave as theta 2, and so on, down to theta n plus 1. And what we needed to do was provide a function called cost function that we would then pass into what we saw earlier. We would use the f min u and c, and then at cost function and so on, right? But the f min u and c was the f min unconstrained, and this was what would, and f min u and c was what would take the cost function and minimize it for us. So the two main things that the cost function needed to return were first jval, and for that we need to write code to compute the cost function j of theta. Now when we're using regularized logistic regression, of course the cost function j of theta changes, and in particular now our cost function needs to include this additional regularization term at the end as well. So when you compute j of theta, be sure to include that term at the end. And then the other thing that this cost function thing needs to provide were the gradients. So gradient 1 needs to be set to the partial derivative of j of theta with respect to theta 0. Gradient 2 needs to be set to that, and so on. And once again, the index is off by 1, right, because of the indexing from 1 that octave uses. And looking at these terms, this term over here, we actually worked this out on a previous slide. It's actually equal to this. It doesn't change because the derivative for theta 0 doesn't change compared to the version without regularization. And the other terms do change, and in particular, the derivative with respect to theta 1, we worked this out on the previous slide as well, is equal to the original term and then minus lambda over m times theta 1. Just so we make sure we pause this correctly, if we can add parentheses here, right, so the summation doesn't extend. And similarly, this other term here looks like this with this additional term that we had on the previous slide that corresponds to the gradient from the regularization objective. So if you implement this cost function and pass this into f min u and c, or to one of those advanced optimization techniques, that will minimize the new regularized cost function j of theta, and the parameters you get out will be the ones that correspond to logistic regression with regularization. So now you know how to implement regularized logistic regression. When I walk around Silicon Valley, I live here in Silicon Valley, there are a lot of engineers that are frankly making a ton of money for their companies using machine learning algorithms. And I know we've only been studying this stuff for a little while, but if you understand linear regression, logistic regression, the advanced optimization algorithms, and regularization, by now, frankly, you probably know quite a lot more machine learning than many, certainly not all, but you probably know quite a lot more machine learning right now than, frankly, many of the Silicon Valley engineers that are out there having very successful careers, making tons of money for the companies, or building great products using machine learning algorithms. So congratulations, you've actually come a long ways, and you actually know enough to apply this stuff and get it to work for many problems. So congratulations for that. But of course, still a lot more that we want to teach you, and in the next set of videos after this, we'll start to talk about a very powerful class of nonlinear classifiers. So whereas linear regression, logistic regression, you can throw in polynomial terms, but it turns out that there are much more powerful nonlinear classifiers that can than sort of polynomial regression. And in the next set of videos after this one, I'll start telling you about them so that you have even more powerful learning algorithms than you have now to apply to different problems.